Now let's figure out the volume of a shape made with the same base region as I drew before, but instead of rotating it around some vertical or horizontal line, I'm going to imagine constructing a solid on that base in a certain way. So I'm trying to make what's really a three-dimensional picture here with three axes, an x-axis kind of coming out of the screen towards you a bit, a y-axis going into the screen a bit, and a third axis you could label it with the letter z, going straight up and down, well, positive z going up. And let me draw in the xy plane, you make these kind of drawings a lot in multivariable calculus, my same curves as before. That curve where y is larger is y equals x squared. This one where y is lower is y equals x cubed. This is x equals 1 right there. This over here is y equals 1. Maybe 1 should be a little further to the left there. I'm creating a solid with a base equal to this crescent shape, such that, listen very carefully, the cross sections perpendicular to the x-axis, meaning I'm slicing the solid this way, are, let's say, equilateral triangles. Other common things to pick are squares, semicircles. Let's say they're equilateral triangles. A typical cross section might look about like this. An equilateral triangle. If you make a bunch of such cross sections, you get the solid. And notice as you approach the corners, they have to get smaller and smaller because they're always equilateral triangles. And the base is changing how long it is. You put all this together and you get like some sort of croissant shape that you want to eat. Okay, is this three-dimensional solid we're about to try to find the volume of. Though its volume is very small, and if I use centimeters, it'd be too small to eat. It would not fill you up at all. So I'm going to say the units are in meters now, and we're going to get a volume in cubic meters that'll fill you up more when you actually eat it. Of course, it'll be very long and skinny at the same time, but at least it will fill your tummy when you eat it. Okay. What's the volume going to be? Think about your cross sections at a certain value of x that are thin and having a width delta x. The cross sections are equilateral triangles. The sides are the same, and the angles are all 60 degrees. Those are the cross sections, equilateral triangles. That have a certain area that depends on x. X is going to vary from 0 to 1 here. Just like before, I could write delta V is approximately A of x times delta x. Or in the infinitesimal version, I could write dv equals A of x dx. The deltas become d's and the approximately equal becomes exactly equal. But to tell you the truth, this is more rigorous math than that is. Still kind of vague because we're not specifying how good the approximation is. That only comes when you specify what the errors behave like. The total volume as a Riemann sum is the sum of the little volumes, which is approximately the sum of A of x times delta x. And therefore, as delta x goes to 0, just like always so far today, the volume will be the integral of A of x. The delta morphs into a d, and the summation sign morphs into an integral sign in your imagination. with the conceptual equation, convenient fiction approach, the volume is the sum of little volumes. You get to the same answer in the end. But then you remind yourself, hey, I needed to do a definite integral. So what does x vary over? It varies over the interval from 0 to 1. So if I can figure out a of x, then I can do this integral. This is way harder than you might imagine at first to do, but we can do it. We need to think about these cross sections to help us figure out a of x. Let's label the length of the side of a cross section. How about L of x like we did before? Let me redraw the triangle down here. It's an equilateral triangle. I could break it apart into two sub-triangles that are both right triangles, and in fact, both 30, 60, 90 triangles. This whole length is L of x, as is, for example, this length. Half the base is therefore going to be L of x divided by 2. You can use facts about 30, 60, 90 triangles to figure out the height. H of x. Or if you don't remember some facts about 30, 60, 90 triangles, you can rederive them using the Pythagorean theorem. Pythagorean theorem implies h of x squared plus, I'm focused on this shorter length down here. I'm focused on this triangle on the left here. L of x divided by 2 squared equals the hypotenuse length squared. Solve for h of x. H of x is going to be, if you simplify that, you get L of x squared over 4. If I subtract that from both sides, I get 3/4 L of x squared. That's h of x squared, sorry. So h of x itself, taking the positive square root, is square root of 3 over 2 times L of x. L of x is positive, so I don't need absolute value signs there. And if you're thinking about facts you may remember from the past about 30, 60, 90 triangles, that's where the square root of 3 over 2 comes from. So that's the height, and therefore the area, the 1/2 base times height, the base is L of x. I'm looking at the big triangle now. The height is square root of 3 over 2 L of x. This simplifies to square root of 3 over 4 L of x squared. But I'm still not done because I got to figure out what L of x is. Well, it's not quite as hard as it sounds. Go back up to your original picture. L of x is this distance right there. Oh, these functions have to be relevant, right? I only thought about those at the beginning so far, but now I'm thinking about them at the end. They've got to be relevant. L of x is this distance. Second coordinate to this point minus second coordinate to that point, x squared minus x cubed. That's L of x. X squared minus x cubed. I've got to square that. Okay, so let's expand this. Square root of 3 over 4. If I expand that, I'll get x to the 4th minus 2x to the 5th plus x to the 6th. I foiled in my head there. And that is a of x. That's the function I get to integrate from 0 to 1. Definitely doable, including by hand. For the sake of time, let's just have Mathematica do it. Integral from 0 to 1 of square root of 3 over 4, which I could factor out in front, x to the 4th minus 2x to the 5th plus x to the 6th. This ends up being a pretty small number, though initially it's going to give us an exact form. As an approximation, that's about 0.004 cubic meters if the length unit was meters. Very small number of cubic meters, but I think that's enough to fill your tummy. Right, 250th of a cubic meter or so. Yeah, that's a good sized croissant. That'll fill you. If it was cubic centimeters, that's not even one bite, barely.